Hello, today I'd like to compute this limit of a sum, which I really enjoyed solving the first time. There is a hint for this which would really help you solve this, and it would be Riemann sums, on which I did a video a couple of days ago. So if you'd like to check that out before you actually try this out yourself, definitely go for it. I think it's a pretty good video to get going on using them in problem solving. So yeah, that's what we're going to do. We're going to use these Riemann sums to compute this limit, and let's see how we can do that. So what I'd like to do first is I'm going to condense this notation a little bit. So we're just going to have the limit as n approaches infinity of n to the power of b divided by n to the power of a, and then we have our sum from, let's see, m equals 1 up to n of m to the power of a divided by the sum from m equals 1 up to n of m to the power of b, of course. So yeah, here we can really see the similarities between our expression and the definition of an integral in terms of a Riemann sum. So that would be the integral from p to q of f of x dx. That would be equal to the limit as n approaches infinity of q minus p divided by n times the sum from m equals 1 up to n of the function f of q plus q minus p times m over n. So what if we were to plug in p equals 0 and q equals 1? So we would just have an integral of a general function f of x dx, but with the bounds 0 to 1. So of course that would simplify a lot of this expression here, so we would of course have this simple integral, or not necessarily, but in this case it will be. And then we have q minus p, which is of course just 1, so we have 1 over n, and in this case we have just m over n, by simplifying the fact that q over there would be 0. Okay, that's nice, but how could we use that in this case? Well, actually, you can see the similarities between this m to the power of b and then of course n to the power of b in the numerator there. And we're going to take advantage of that. So we're actually going to take these powers and we're going to put them in the denominator and the numerator separately. So we would have the limit as n approaches infinity of 1 over n to the power of a times the sum from m equals 1 up to n of m to the power of a divided by 1 over n to the power of b times the sum from m equals 1 up to n of m to the power of b, of course. Notice that our 1 over n to the power of a is just put in front in the numerator there, and then we just divide by n to the power of b, and we get this expression over here. Now, since this doesn't actually depend on m, we can just take it inside the sum, and the same goes for this. So then we would just get, since they both have to the power of a, we just have m divided by n to the power of a, and over here. Now, at this point, it's really clear that these two sums closely resemble our definition of a Riemann sum, but we still need to do a couple of things. First of all, we're missing this 1 over n. So that's not hard to fix, because we can just multiply both sides, the numerator and the denominator, by 1 over n. So we would just have 1 over n in the numerator over there and over here, and that would fix everything. Now we can just take this limit and split it up into our two parts of the fraction. So we would have the limit as n approaches infinity of 1 over n times the sum from m equals 1 up to n of m over n to the power of a, and the same thing goes for our case with b. Now, of course, comes the fun part. At this point, we're just going to have to choose a smart function f, because as you can see, basically all parts are perfectly aligning here. We've got our limits, we've got 1 over n, we've got our sum, and we have something inside m over n. So basically, we're just going to have to choose the function x to the power of a for our numerator. And for our denominator, we're just going to have to choose x to the power of b. So in this case, we would have something like the integral from 0 to 1 of x to the power of a dx, and that would be equal to the limit as n approaches infinity of 1 over n times our sum from m equals 1 up to n of m over n to the power of a. And that's really nice because we can get rid of the limits and just convert this into a fraction of integrals. So the integral from 0 to 1 of x to the power of a dx divided by the integral from 0 to 1 of x to the power of b dx. Now, of course, these integrals are the exact same, so I'll go through them quickly, and they're also really quite basic because they're just a power rule. So we're just going to evaluate x to the power of a plus 1 divided by a plus 1 from 0 to 1, and the same thing is going to go for our b case, but quickly, of course, 1 to any power is just going to be 1, and if we plug in x equals 0, we're just going to get 0. So basically, this whole thing just collapses to 1 over a plus 1. And we're going to get the same thing in the denominator for b, 1 over b plus 1. And in the end, we're going to get b plus 1 divided by a plus 1. And that is a really nice expression for a really complicated sum, of course. Now, it is important that both b and a are strictly bigger than minus 1, otherwise this won't converge. But I really think that this was a nice exercise using Riemann sums and a good example of why they're so cool. We're basically turning boring limits and sums into integrals, which are fun. So yeah, thank you so much for watching. Till next time, and if you want to see something about Riemann sums, definitely watch the video linked down below. So thank you so much for watching. Till next time.